decent chance at winning.
Yeah,
So
I'll add for anybody out there that the Corn Hacks is an excellent opportunity. I've done judging on and off for how I think this is the fifth year that they've done it, and so, some of the I mean some of the projects are absolutely outstanding. Some of them, are not that great, but it doesn't matter. In fact, I would say that you should go to this and do it just for, well, like you said, for the swag, for the free food, but also just for the experience. It's just a fun thing to get the semester kicked off. It's the Friday and Saturday right after the first week of class, so presumably you're not that busy yet, and that's the perfect time to do it. And yeah, you do stay up 24 hours. You can sleep, you can leave and go back home. Of course, you're not there up for you're not expected to be up for 24 hours like a lock-in or something like that. But it is a good opportunity. UNLcornhacks.com is the actual website. You can go ahead and sign up anytime between now and presumably a week beforehand or something like that. Yeah.
and one more thing is that hopefully we will get a lot of sponsors, and so this is going to be a good opportunity to get like internships as well.
Yep. They're who are the sponsors right now? Okay.
I'm currently working on getting sponsors, so
Okay.
that's TBD,
All
but
right.
hopefully we'll get a couple good ones.
Where's the $3,000 coming from there? If you don't have
Future,
sponsors.
future use like past. Oh no! Sorry, not future, past.
Ah, okay. Okay.
You have leftover funds.
All right.
If worst comes to worst, we'll be fine.
I owe you one prize money.
Yeah, you get $10. Congrats.
Yeah.
Okay, really quick, can I ask for like what's something somebody does done in the past, just so I understand like the scale of
I'm not too sure. I've never done this before.
So the best project that I've ever seen that won the first year I did it was they put together an Arduino. They basically, without knowing it, they cloned Pi-hole. Do you know what Pi-hole is?
Yeah.
So Pi-hole is it's a Raspberry Pi, but it's a program. So you've got ad blockers on a browser, right? But that doesn't prevent hardware ads. So, for example, all the new Samsung TVs that come out, right? You go to the menu and you've got goddamn ads on a TV that you just paid for. And Pi-hole is designed to block all ads at the hardware level, at the network level, and then send it down into the Pi-hole, and also spoof that, oh yeah, that ad was delivered. Don't worry about it. And anyway, they did it, but they did it for Spotify. So Spotify commercials would come up, it would play an alternative song instead. And it would block all the commercials, basically. They put this together in about 24 hours. Another hardware version, one that I saw last year, I believe that they created their own dorm door, not doorbell, yeah, that did something. It triggered some other hardware somewhere else to let them know, or it was like basically kind of like a trick or treat or something, like and it'd give out some candy or something. I don't know. People have made games really quick. That's maybe what they were going with the retro theme. Build a side-scrolling 8-bit game. Other people have made study tools, just proof of concept kind of stuff. A lot of people just use it as an opportunity to say, I want to learn Android App Studio. All right, well, let's just build an app, and we'll use this as an opportunity to throw something together and learn along the way in a compressed 24-hour period. You can do it individually. You can do it as a team. You can maybe meet somebody there and then team up. I'm not sure. That'd be a question for John.
Yeah.
You can? Okay. But at the very least, you get food. you can hang out with people. So yeah, it's Corn Hacks. It's been going on. This is the 5th annual. Do you know? I have no idea. At least 4th annual. I'm not sure. You could probably look at old events somewhere. Maybe not. I don't know. But last year it was 100% virtual. This year it sounds like it's going to be, well, hopefully in person.
Unless we hear at the last minute it can't be.
Okay. All right. So yeah, corn hacks, unlcornhacks.com.
And I'll put a new poster on the also.
Okay.
So y'all can get the actual link.
All right. Cool. Thank you. And to continue from last time, we're going to actually show probably one reduction today. But again, these are mapping reductions. So what we're trying to do is we're trying to prove NP completeness. Now, let's understand again what a mapping reduction is before we go into this presentation. Again, what you're trying to do is you're trying to transform one problem into another problem. If you look at this as a language, say L1 and L2, a language partitions the set of all strings up, like this is the set of all strings here, an infinite set. It partitions it up into two sets, yes instances and no instances. And what a mapping reduction does, or a mapping between these two languages, is it maps all yes instances to yes instances over here, and all no instances to no instances over here. That's with respect to languages, right? You're mapping strings to strings, right? This is a strings x to strings y. That's the abstract way of thinking about it, because again, algorithms solve problems. When you translate that to mathematics, that is Turing machines decide languages. And so problems here are languages. Now let's look at it with respect to problems. If I've got a problem A over here and a problem B, B over here, a reduction simply takes a yes instance over here and applies it to some yes instance over here. And it takes, here, I had the diagram before. No, I don't have it. Look at this as all possible inputs over here. You're mapping x to y, and then you're using the supposed solution for b sub x. If that says yes, well, if this is a valid transformation here, then this will be true if and only if the purported solution for a says yes and no likewise. Right? When I started motivating this, we looked at the following three problems. Is path? We reduce to get path. Right? And we reduce that further to shortest path. How did we do that? We used a solution for this, say Dijkstra's, and Dijkstra's outputs this path P, and then we gave that back over here to this algorithm over here. In fact, let me redraw that. Right? We took that and we placed it back over here, and we just asked a question, right? Is that none, or is that, or actually we just returned path. That was also, the shortest path will be a path, so that is a solution to this problem. And by using that, we put it back over here to is path, and we simply said, if P is not null, or none, then yes, else no, right? So we were, by reduction, we're taking something that is difficult or easy, whatever its complexity is, and we are transforming it into something that is possibly more complex, because if we can solve something that's more complex, intuitively we can solve something that's even easier. Now again, the way that I drew them eventually was vertically. Not like this, but is path reduces to get path, which reduces to shortest path. And that's where we get this, harder question, and I'll put that in the quotes up here and down here, easier, because it's not necessarily harder, it's not necessarily easier. In fact, you can, a lot of the times it takes a little bit of a trick to reduce down to the other way. but it is usually, especially if we're talking about all these problems in P or NP complete problems, then they all reduce to each other anyway, some way, right? But coming up with a direct path down here, that might be the tricky part. These were the trivially easy parts that we could do, right? So again, a reduction goes up. It takes something that's easier and potentially makes it harder. Because if you can solve this harder problem, then it's even easier to solve this easier problem down here. And like you put it the other day, it's a reduction in the sense that you are reducing your work down to another problem. Instead of writing 1, 2, and 3 functions, no, I'm going to use this function to call this function. I'm going to use this function to call this function, and that reduces my work, right? Instead of writing 3 pieces of code, now I only have to write 1 piece of code, right? Likewise with NP-complete problems, right? Remember this landscape here? NP-complete problems. If I have a solution to one of them, then I've reduced this entire domain here down to this one problem, right? And one solution to that one problem solves everything, right? So you've reduced your infinite amount of work and an infinite amount of code that you have to write, and you've reduced it down to one function that you have to write, right? Okay, with that idea, let's introduce the clique problem. So, a clique in a graph G equals V comma E is a subset of vertices, and I'll go ahead and label it as C, right? Why? Because it's called a clique. Some people would pronounce it clique, right? In real life, what is a clique? If somebody's acting, or if a group of people is acting cliquish, they are very, 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 very close, and they're not close to anybody outside the clique, or the clique, whatever you want to call it, right? It is a set of vertices that are all connected. That is, for all pairs x and y in the clique, you have that x and y are connected by an edge in G. Okay? Now, they could be connected to things outside, fine, but the clique itself is a complete subgraph, is what it's sometimes called. Okay? Finding the maximum cliques, maximal clique, is an NP complete problem. It is very, very difficult. All right? Now, why do you go for maximal? Well, you can always go for minimal. What trivially can you do? Take one vertex, right? Vacuously, it's connected to itself. Or and so you can always find a minimal clique. The maximum value of any clique, though, max possible, is what? Number of vertices. Right? It could be that you have an entire graph G that is a complete graph on n vertices. So if G is equal to k sub n, that's the complete graph on n vertices. Right? Complete probably because K, German, complete, I don't know. Okay, so do we want an example? Or I guess I gave one last time, right? Yeah, go ahead. All right. There. Now, what about these 3 vertices? Does that form a clique? Nope. Because these 2 are not connected, these 2 are not connected. These 2 are, but so what? The other 2 are not. What is the maximal clique here? 4, and they're all right here. Right? That is a complete subgraph here. Is there any one that's bigger? Not in this particular case. Okay. So this is a clique of k being size 4, lowercase k here. Okay. Now, given a graph G, you want to find k the maximal clique. That is a functional version, or that is an optimization version. Here's G, you tell me K, the maximum size of the clique, right? What we want to do is we want to transform this to a decision version because we want yes or no answers. So what I'm going to do is I'm going to define the clique problem to be a language problem. That's an encoding of a graph G along with a K such that there is a clique of size K in G. Sometimes this is called parameterization. We're just simply taking the optimization or the functional version or whatever other version you've got here, and we are transforming it into a decision version, a yes or no question. Does there exist a clique of size K in this graph G? I don't know what it is, but we can ask an oracle. Yes, there is. No, there's not. That doesn't help us necessarily to get to what that clique is, but if you had a solution to this, you could easily find a clique of size K by simply just building subsets and building subgraphs off of it. We won't get into that though. Okay? So it is enough to consider G and a fixed K here. What if you did have an answer here, like a solution here that kept saying yes or no, yes or no? How could I find the best K? Yeah, for K being n down to 1, if, say that I've got this C that takes G and K, if C sub G K accepts output K. That's it. In fact, you can make this even more efficient. How? By doing binary search. Right? Start in the middle. Do you have a clique of at least size n divided by 2? Right? Yes? Oh, okay. I'll go ahead and go over here. Do you have a clique of size n divided by 3/4 n? Right? And if the answer was no, then go down because that's going to be, you don't have a clique of that size, whatever. Right? In that case, you might want to say that there is a clique of at least size K there, right? If you want the optimization version. That's just a small technical detail. If you didn't have it, then you couldn't use binary search, but this solution that you just suggested would work just as well. Okay? All right. So I want to go through our 5-step process here to show this. We want to first show that the problem, the clique problem now, is in NP, because if it's not within the world that we're currently considering, if it's exponential time or even above, or if it's not even decidable, it's like the halting problem, then we're stuck already. It can't be NP complete if it's not already in NP. So 1, show that the clique problem is in NP by coming up with a non-deterministic polynomial time algorithm for it. So step 1, all we have to do is develop a non-deterministic polynomial time algorithm for the clique problem. What's my input? A graph G and an integer K, and my output will be except if there is a clique of size K in G. Right? Okay, I want to make sure I'm good on time here. All right, so what do? 1, with any non-deterministic algorithm, you have 2 phases. You guess a solution, and then you verify a solution. So what am I guessing here? Guess a subset of vertices of size K. In other words, the cardinality of this set is K. Right? And the key word here is guess. That's what makes this non-deterministic. It's not randomized. It's not a loop that goes over every single possible guess like it would be with a brute force solution. It is simply just one guess. 2, verify. Verify. Right? For each pair, x and y, in that subset, if that is not an edge, x comma y, If that is not an edge, then do we accept that this is a certificate, that it's a witness to the fact that there is a set of a clique of size k? Or sorry, if it's not an edge, is what I said, I think. I just didn't write it like that. So here are 3 vertices that I guessed. Oh, that edge is not there. Nope, that's not a solution. So, reject. And when we say reject, we also mean stop and reject, a halt, right? Otherwise, if they're all there, guess what? Accept. Why does that work? Well, it's because our guess was a subset of size k. And if we get out of this for loop here without ever rejecting, that means that all the pairs in that subset are connected, and it forms a clique of size k. Now, again, the way that you view this non-determinism is by viewing it as this big giant computation tree, and your computation time is with respect to the depth of that tree. You don't have to check every single possible exponentially sized exponential number of leaves. The acceptance property is, does there exist a leaf that accepts? And if there is, then you accept, then the entire machine accepts. It's magic. Right? So clearly this is non-deterministic. So A, clearly it is non-deterministic. Right? That's the guess part right here. And B, clearly it's going to be order what? K. Why? Well, actually, technically what? All right, so the non-determinism, that'll be order K. But verification, well, you only go over for each pair in a set of size K. So what's that going to be? Order K squared. In either case, K is bounded by order N, right? Because that's the maximum clique that you can have. That's why I asked that question over here, right? And so therefore, each one of these is bounded by order N squared and order N. Okay? So it's polynomial, right? And it is non-deterministic. Guess what? That's NP.
So is K decided by the no,
K is part of the input. Yep.
Okay.
Yeah.
How does this even answer our question though? Because if it halts, it doesn't tell us if there is one. It just tells us that.
If one of the leaves accepts, the entire machine accepts.
So do we check the entire all of the leaves now?
Nope. So one way I've thought about it that is kind of cartoonish is, you know, like a typical superhero that's able, like Multiple Man, right? So it's kind of like parallelism, right? In that you can make multiple copies, like if there are 5 different possible solutions. Farm it out to processor A, B, C, and D, and E. And then you all come together and say, I found a solution, or I didn't find a solution, I didn't find one, I found one, I didn't find one, I didn't find one. If at least one of them found a solution, you take a big giant disjunction of all of them, right? That's what a universal, that's what an existential quantifier does, right? But you don't have to pay for the parallelism. You only pay for what each one does, the depth. And then you magically bring them all together. It's like Multiple Man going out and you know, splitting himself into 200 people, and then coming back into one person, and he has the knowledge of all 200 of them. Right? Again, it's magic. It is not a real computational model. It is a way of thinking about the power of an existential quantifier in logic. Right? It can magically do a big giant disjunction over an exponential number of items. Right? Yeah.
So it's less of like the computer looking at the problem and just making like an actual like human guess, where it's just like, I think it might be this one, but I'm not.
Yeah, and then it all comes together, and if at least one of them said, I found it, right, then the entire thing says, I found it. So again, I don't know if that Multiple Man kind of
Actually,
idea helps,
sort of
but
running through it. So it actually is sort of running through all of them, or it's just
You can simulate running through all of them by using an exponential time algorithm, right?
Right, but like when you were describing the guess, right?
Mm-hmm.
But that still seems like the computer's running through a lot of different.
Think of it as an exponential number of computers that then magically get merged together into one computer, and it has the results of all of them.
So it still has all that data. It just took, like the time.
Exactly. It only takes the depth rather than the width of the tree.
Okay, cool.
Okay. All right. So 2, select a known NP-complete problem to reduce from. That we're going to do with SAT because that's the first one and that's the only one that we know about yet. Right? But I'm going to do a very, very specific version of SAT. It's a 3 CNF SAT. So 3 means, actually let me define CNF first. This is conjunctive normal form. And the 3 means that each clause, I'll define clause here in a second, has at most, or exactly if you want to, 3 variables, or their negations. All right? This is my choice for an NP-complete problem. A non-trivial fact is that you can take any SAT formula and reformulate the logic by factoring out commonalities and splitting things up so that it conforms to this 3 CNF format. What does a 3 CNF format look like? Well, let me get to the right class here. And there we go. There's one. So this is each one of these is a clause. Clause 1. Clause 2. And clause 3. Right? In general, you can have K clauses. Right? But each clause only has 3 variables or their negations, right? 1, 2, 3, 1, 2, 3, 1, 2, 3. Not only that, but you take the disjunction, or sorry, this is the conjunction. That's why we call it CNF, conjunctive normal form. You take all the clauses and you AND them together. Not only that, but each clause is only a disjunction. Disjunction. Or. Right? So this is a very, very specific format of a logical statement. But you can take any logical statement and restate it as an equivalent 3 CNF form. Right? This is like a normalization. Just take my word for it for now. Right? Yeah.
So does there have to be 3 clauses?
No. In general, there are K clauses. Right? I just wrote 3 here because the reduction that I'm about to show you would get very it's already messy, but it would get way more messy if we had more than 3 clauses.
Okay.
And then it'd get way too trivial if we only had 2 clauses. So this is the sweet spot. Okay? So that was 2. 3, step 3. What I need to do is I need to come up with a mapping reduction that maps my known NP-complete problem to this problem. In other words, I need to come up with a reduction that takes a general 3 CNF formula and transforms it into a graph G such that phi is satisfiable if and only if G has a clique. Okay? And implicitly here, K will be the number of clauses in this first one, and it'll also be the number or the size of the clique in this one. Right? Now, why does this help me? Again, remember, this is NP complete. Ultimately, what I'm going to be showing here is that this is NP complete. Now, why? Think of it in terms of this mapping here. If I take a 3CNF formula and I transform it into a graph, and then suppose I have this really cool state-of-the-art algorithm over here, algo whatever, that takes a graph G and outputs yes if it has a clause, or if it, sorry, not a clause, if it has a clique of size k. Right? How could I use that to solve this problem down here? Here's my problem for SAT solution. Right? 1, convert the SAT formula into a 3CNF formula. Right? And I'll call it phi. Right? 2, map phi to G. 3, if algo on G accepts, else reject. There's my algorithm for another NP complete problem. Now, if this runs in polynomial time, guess what? I just showed that P is equal to NP. If this runs in exponential time, have I shown anything? Nothing surprising, right? Because you can always simulate non-determinism with an exponential amount of time. Right? But I have solved the original problem without actually writing a function to do it, without writing Python code to do it. All I did was take its input and transform it into a different piece of input, and then I used the algorithm there. Just like I did with respect to, way back here, with respect to these. I just took an input and I translated it to some other input because I was lazy and I didn't want to write an algorithm for this one down here. And finally, when I got to the end of the road here, then, yeah, okay, fine, I'm going to have to write Dijkstra's algorithm now. But I didn't have to write 3 algorithms. I only had to write 1 algorithm to rule them all. Right?
So
Yeah.
But in that picture you had arrows pointing up.
Yep, that's the reduction. Reductions
yeah,
go up.
Like, so we already have the phi.
But the phi is our input because we want a SAT solver. So we transform it to another algorithm, and okay, fine. Now I'll write Dijkstra's, or I'll write this algorithm that solves the clique problem. Now I do actually have to implement this.
I thought our goal was to not have to write that row.
Well, our goal is not to have to write the SAT solver, and I didn't, right?
Oh.
All I'm doing is map it and then call this other function over here.
So you're mapping phi to the SAT problem?
No, the phi the SAT problem to G the graph problem. I'm transforming the graph. I'm reducing the problem down to this other problem over here.
How do you turn phi to the graph?
That's step
Okay.
4. Exactly. Right? So the mapping here is going to do a couple of things. First of all, let me see. So we define, so given phi, which is a collection of clauses, disjunction, or conjunction, conjunction of C sub k, right? We construct a graph that has a clique of size k if and only if it's satisfiable. The way that we do that is for each clause, and for that I'm going to label it as, how do I label it here? C sub I is going to be x sub I, or x sub I, x1, x2, x3. I'll superscript them with i's, right? Or, right? There we go. For each clause that's labeled like that, create 3 vertices. x1, x2, x3, all labeled with I above it. Okay? Yep. Okay, in the write-up, I make this even more explicit by calling them V's instead. V, V, V. These are vertices. Okay? Oh. Remember, we are online, so if you have any questions, go ahead and post there. Nobody's posted any questions, though. Okay. Excuse me. And then 2, that's all the vertices. So if we have k clauses, 3 vertices for each one, then that means we have 3k vertices in our resulting graph. Now, what about edges? Yeah, go ahead.
So the vertices are each of the 3 like things in the clause, right?
Right. I'll show you an example here in a second. Right. But what we need is our edges. So if vertices, so we draw edges if both the following hold. If the edges are in different, x's are in different clauses, and 2, so A and B, they are not negations of each other. Okay? Now, let's go ahead and look at an example. And the example I'm going to use is the one that we just looked at. Here is one possibility. Here's one possible input. I am going to write vertices for each one of these things. So let's do the first clause over here. I'll label it even, C1. I'm going to create 3 vertices representing x1, not x2, and x3. I'm going to do C2 and C3 as well. C2 is up here, and it's got 3 vertices, x1, not x2, and not x3. I wonder if I can get this to look nicer. Okay. There we go. x1. I guess it doesn't look that nice. x2 and x3. I can't get the sizes correct. All right. Now, how do I draw edges? Well, first of all, do I draw an edge between these two? Remember, they have to be in different clauses. So inside of this clause, I would never, inside of this clause right here, I would never have any edges at all. They would only go from one clause to another clause, or to this clause over here, or between those two. Right? They would never go within. None of these vertices would ever be, or none of these edges would ever be here. Okay? So, x1, does it get connected to this one? Yes, because it's not the negation of x1. Nor is this the negation of x1, nor is this the negation of x1. Right? What about, yeah, go ahead. All 3 of those are connected. Now, what about this one right here? Well, it goes to x1 and x3, not x3, because, of course, they're not even the same variable. But what about to this one? Well, yeah, because it's not the negation of it. Okay? What about x3 will go to the first 2, of course, because it is not even the same variable. But what about this one right here? x3 to not x3. Do I connect those? Nope. Because they are negations of each other. I only connect it if they're not negations of each other. So that does not get put there. If we want to, we can go ahead and keep it there, but explicitly say that that's actually one that's not there. Okay? Yeah?
So these X's still vertices, right?
Yeah, relabel them as V's. I'm doing this so that we don't lose sight of the fact that they're still up here.
So what does negation of the vertices means?
So x1 and x2, or sorry, x1 and not x1. Those are the negations of each other, right?
How is that represented in the graph, or is it
It's represented by not putting that edge there, meaning that ultimately they're not going to be participants in any clique, right? Because that edge is not there. Now map that back to, now this is step 4 that we're going to prove this, but, or I guess we're still on step 3, yeah. Anyway, why is that relevant to the original logical statement. If I set x3 to be true, what does that mean for it in this clause over here? It necessarily has to be false, meaning that this one cannot make this clause true, right? If I set this to false, then that means that this is true, and so it's okay for this clause, but that means that it kills it for this clause. And I have to find one of the other two to be true in the original logical statement, or with respect to the graph, I have to get an edge to connect them for it to be a clique. Yeah?
So wait, to summarize, for a clique to exist, you would need an assignment for each of the three variables.
Exactly.
And they would need to be disjoint so that it's satisfied.
Exactly. Right? And they would need to be consistent, is what we would say. Because you can't assign, both of these cannot be true. Right?
Oh.
x3 and not x3, that's a contradiction.
And so by connecting all the ones from all the different clauses except the ones that like directly negate, like the except for negating or connecting xk and not xk, you're making it so that the only ones that form a clique will be the ones that are consistent with each other.
Exactly. And what does that look like in the original clause? It's going to be true, true, true somewhere over here, making the entire thing satisfiable. True and true and true, that'll be satisfiable. Right. So let me finish the picture here. What about the, did I do them all? I think so. I need 3 here though. There we go. All right, now between clause 1 and clause 3, this one would go to all 3. Okay. This one would go, or x2 would go to x1, but not x2, and this one would go to all 3. All right. So now, give me a satisfying assignment up here in the clause. Give me vertice. Give me variables that I could set to true. Right? True, true. Well, true. It's kind of trivial, right? But that means that these guys all happen to form a what? A clique. That's small. A clique of size. What? Nope, not in this graph. They're all distinct vertices. It's a clique of size 3. How many clauses were in the original? 3. If you did this for k clauses, each clause would have to have at least one satisfied variable, and therefore would necessarily be connected in this gadget that you've just built. This is a graph gadget, right?
So you're saying is that if the statement is satisfiable, it'll have, when you set it up like this, it'll have a clique of at least k, but it could
Well, it'll have a clique. It could be larger. There could be cliques that are smaller. We don't care. We just want, is there a clique of k? Period. Because we transform this into a decision version.
yeah.
Right? There. Does there exist a clique of size k and g? Right? And so my last claim here, and I kind of gave the intuition here, for phi has a satisfying assignment if and only if G has a clique of size k. And it's by construction, but of course you would need to go through a full proof. Okay, I think there's the proof since we're low on time here, right? It's just by construction. Then I go the other way because it's an if and only if statement. I will show a full proof of the next reduction that we're going to do for step 4. But in the time that we do have remaining here, step 5. Is this polynomial? That was the reduction.
Oh, yeah.
That's my reduction. Right? I took an input to these 3 CNF problem, and I transformed it into a graph problem. Right? There are other cliques in here to answer your other question. Give me another one. So if I set x3 here to be, x3 and x3, that would correspond to x3 here and x3 here. And guess what? They are connected. And then I couldn't do it for x3 on this one because that would be inconsistent. But I could do it on x1, or let's do x2. But now for this one, I of course would set it to be false because I want this to be true. And so that corresponds to this guy right here. Guess what? That's connected, and that's connected. Right? So any satisfying assignment will correspond to a clique of size k. Yeah.
I was just wondering, is there like a, for the homework, we aren't just working with graphs, proving graphs or anything, but, I don't know whether that's true, that was actually a question, but like,
I don't think I asked you to show anything too complicated.
I guess my real question is just that like, is there like a general way we could know how to like work the question we're trying to do into a SAT problem?
Not really. You always look for the easiest reduction. And like an old math professor once told me when I asked him, well, what's the intuition behind solving degree k homogeneous recurrence relations? Why do you search for solutions of this form? Why do you search for solutions of that form, right? If you've ever taken differential equations, right? They've got this big giant chart of if your formula looks like this, your solution will have a form like this. Like, explain that to me, right? And then they've got this big giant chart of if A, then B, if B, then C, if D, then E. And by the way, if it's not on here, then good luck, right? And I asked him, he goes, well, people just came up with them. He goes, you sit there and you stare at it and you try 50 different things, and the first 49 didn't work, the 50th one did, and you call it a day.
So this is why you said the programming part was the easiest part of this assignment?
Yeah, well, I didn't give you anything difficult. I'll say that much.
Okay, so
You should be,
you have
yeah.
to take the SAT thing.
No. I'm not asking you to do anything from SAT. In fact, I think all of them I tell you, try to reduce from this problem over here because that's the easiest one.
Okay.
Right? I'm giving you a strong hint there. Anyway, my claim that it's a polynomial is pretty hopefully clear, right? We're taking a SAT formula of size C1 and C2 ... and CK, and I'm outputting a graph such that G equals V comma E. How big is the vertex set? Well, 3K, right? And if K is my input size to the first one, it's actually not, it's the number of variables, but K is at most N, then this is certainly going to be bounded by order N. And then the edge set, of course, since the vertex set is bounded by N, then the edge set is going to be bounded by order N squared. And I didn't do any guessing. There was no non-determinism in this mapping here, right? It was just a for each, right? For each edge, then for each vertex, ask this question and this question, and if they both hold, then draw the edge or output the edge. Right? And this is why it's called a mapping reduction, because I didn't actually come up with this algorithm right here. All I did was come up with the mapping between the two problems. I still don't know how to solve the clique problem. Nobody knows how to solve the clique problem efficiently. Of course, we could all come up with a very straightforward brute force solution that would be exponential time, but nobody knows how to do it. Right? But I do know how to do this reduction. Right? So that if anybody ever does come up with this algorithm, hey, great. I've solved a million other problems already by reducing that to this one. So any questions? Otherwise, I'll show you another reduction next time. It's called the vertex cover problem. So let's look at another graph here. The same graph as before. I don't know if I can draw it from memory, but this might be it. There we go. All right. Vertex cover. Now this is another graph problem. So I'm going to reduce the clique problem to this problem, showing you that transitive relation, that you can go from sat to 3CNF, 3CNF to clique, clique to vertex cover, showing this, showing that because sat is NP complete, this one must necessarily be over here NP complete, right? By transitivity. Now, what is a vertex cover? What you want to do is you want to select a subset of vertices that cover all the edges. So, for example, let's take this one, and this one. Are all the are all the edges covered?
What do you mean by covered edges?
So, look at all the ones that are in its neighborhood, right? This is what a cover is. So, that's covered, that's covered, that's covered. That's covered. That's covered, that's covered, that's covered. Are all the edges covered though? Nope. So what else could I add to add that to get them all covered? What if I added this one? That covers that one and that one and that one, but this one's still not covered. So I need one more. 1, 2, 3, 4, 5. Is that the best you can do?
No, I think that is.
Is it?
Because you need at least 2 on the right to cover those edges. And then something you do with
I could get away with this and this. And then I would need, no, I could get away with 4. Right?
Okay.
So 4 is better. Can you name that tune in 3? Does everybody know what Name That Tune is? It's a really, really old game show, right? They'd say, yeah, they would give you a hint as to what the song was, and then you'd say, I can name that tune in 5 notes. I can name that tune in 1 note. Okay, go ahead and name that tune, right?
There's one edge you didn't cover, so
Oh, which one?
slash top left to bottom right.
Top left to the bottom right. Ooh, you're right.
Right.
Yeah, you're right. Sorry, I lied. So 4. I'll leave that as a question mark. I don't know. Go ahead and try it yourself over the weekend.